So without further ado, I hand it on to Verdun.
Woohoo! Hi everyone. Thank you all for coming. Thank you also to Chandrika and Yeshi for organizing all of this, as well as to Andrea and Sophia for TAing. It's a dreary Saturday morning, and I'm sure you all have been watching Netflix or sleeping in, so I appreciate that you guys have all come out and that you are excited to learn about machine learning, I hope. So my name is Vedant Misra. I work at HubSpot on machine learning. I'll give you a quick background of myself. So I studied physics and math at Columbia. After that, I worked on complex systems research at a think tank called Nexi, where I worked on financial sort of time series analysis with high-resolution time series for different banks and government institutions. After that, I started a company called Kenvi, focused on machine learning for marketing automation. And last year, we were acquired by HubSpot. And I now work at HubSpot on natural language processing, kind of at the intersection of research and product. And I'm really excited about language data in particular, which is what natural language processing is all about. And we're going to be working with some language data later, hopefully. Language data is exciting because it's kind of, language is how we encode our thoughts, right? So we can solve language, we can solve artificial intelligence. And that theme is kind of going to be apparent as we progress through the material. So, quick overview of the agenda. So I'll be talking through some slides for about 20 minutes. After that, we're going to be hands-on keyboard for about an hour, kind of ramping up on the basics of Python, and then building a machine learning pipeline end-to-end. So I'm assuming that the audience has no background at all in Python or machine learning or anything. So it's going to be, in the beginning, definitely a little rudimentary, but we're going to build up all the stuff that you need to actually start doing machine learning in Python in a real sort of production environment. So yeah, 20 minutes of Python basics. We'll use Colab. We'll talk about operators, variables, data types, control flow, all these terms that probably sound kind of alien right now. Then we'll build a machine learning pipeline where we'll do exploratory data analysis, feature selection, model training, and learn about metrics. And for that, we're going to use NumPy and Pandas, both Python libraries. And then we're going to switch gears and build a little bit of an intuition for what machine learning is doing, and how it works. And at the end, kind of wrap up with some deep learning in TensorFlow. Also, feel free to raise your hand if you have any questions. It's going to be probably uncomfortably fast, and it might feel at times like you're just kind of copy-pasting stuff. But the goal is to sort of get you exposed to a lot of different ideas and kind of go breadth first. And then after that, the idea is we're going to form groups and work on projects of our own. So I've prepared some data that you guys can download. You can also feel free to download other data from elsewhere. I don't know how this is going to work because at that point we will have had exactly 2 hours of experience programming. But that's why we have TAs. Hopefully they can help us figure it out. And if we end up all stalled, that's fine. You'll have all of this code after you leave, and you can tinker around with this stuff as you see fit. And so the structure of that is just going to be, for those presentations, for the quick presentations, is I can go over this after lecture as well, but we'll form small teams, select a data set, select something that you want to predict, and then just work through a Colab notebook as we will over the next couple of hours with that data set. And then at the end, the idea is that we'll all just kind of go through, share our screens, and just present what we've done in Colab, what each group has done. And that should be hopefully a good forcing function to get everyone to produce something, or at least try to produce something, and then tell us what issues they have. Okay, so what we're going to do next is I'm going to ask you guys to open up your computers, pull up Chrome or another browser, and head over to this URL, which is also written up there. And then sign into Google if you haven't already, and click on a new Python 3 notebook. And the other thing you're going to do in another tab or in ideally in a window that you can kind of look at on the side is pull up that second URL, tinyurl.com/sloanml notebook. So what's going to be happening is that I'm going to be live coding in that second notebook, and you guys are going to be following along in your own notebooks that you made. So you'll be able to see what I'm doing in my notebook up here, And you'll also be able to see it on your screen, and you can just copy paste stuff out of that. So I'll let you guys get started on this and pull up that notebook. Andrea's going to go around and make sure everyone's doing okay. And I'm going to jump into some actual content. So I think I want to start with talking about why machine learning is interesting. This is Dimas Hassabis. If you don't know who he is, he's the founder of DeepMind, which is a company based in London that was acquired by Google for $500 million a few years ago. Their mission, which he's stating at this talk here, step 1 is to solve intelligence, and step 2 is to use it to solve everything else. So what does that mean? This, I think, is the main point of machine learning. There's trillions of dollars of value probably to be created by making products for people using machine learning, but that is nothing compared to the infinite value that could potentially be unlocked from solving intelligence. So what does that look like? Imagine by 2040, DeepMind has built this machine learning system. It's a set of machine learning models that all work together, and it's trained on like petabytes of language and image data, and you can just ask it questions and get answers. It's pretty amazing, and it has all of the internet and all of sort of scientific data at its disposal. But the problem is we've been stuck for a little while because this system cannot recombine knowledge. It can't give us new information. It can't form new abstractions. And then, someday someone changes something in the representation layer of this machine learning system, and it starts to reconfigure itself. It starts to reconfigure its own abstractions. It starts to become smarter. And then overnight, you have superintelligence. And what that means is you have this intelligent, non-organic system that is autonomously self-optimizing. And soon, what's going to happen is that its factual knowledge will dramatically be beyond that of all of humanity. And we can ask it questions, it processes information, and just gives us answers. We ask it how to cure aging, and it teaches us how to modify our immune systems to clean up all the byproducts of aging, and very quickly, natural human lifespans are 4 digits long. Right? So this sounds kind of crazy, but it's actually, this could happen. We could end up with limitless efficient energy, intelligent autonomous robots that manufacture all our stuff and deliver it globally, and there's no scarcity for goods or services anywhere. This is a feasible outcome. People spend their time however they want, living their 4-digit lifespans, whether they're colonizing the galaxy or playing video games. So this sounds like, what are you talking about? The reason this sounds crazy is because we're sitting on top of an exponential growth curve, and it doesn't know what you can't tell what an exponential growth curve looks like when you're zoomed into it. So what do I mean by that? The main driver behind all this progress is cheap computational power, which is Moore's law. So what's been happening is that every 18 months, the number of transistors on a chip doubles. So you get basically twice as much compute power every 18 months for the same price. This has been going on since the 60s. It might slow down, but it's been pretty consistently accelerating. And so why am I telling you this? Because this is how we can understand the way that exponential growth works. So this is a nice representation I found online. Suppose it's 1940 and Lake Michigan has been completely emptied, and our task is to fill it up. So we can add 1 fluid ounce of water on day 1, and adding 1 fluid ounce of water is equal to adding 1 calculation per second in compute capacity. So in 1940, that was where we were. We had 1 calculation per second in compute capacity. 18 months later, you can add 2 ounces. 18 months later, you can add 4 ounces of water. It's 128 ounces in a gallon. So this is very small amounts of water, right? By 1950, you have about a gallon. By 1970, you have like a small swimming pool. And then if you just keep the clock running, skip ahead to 2000, at this point you have 2 trillion calculations per second. Seems like a lot, but Lake Michigan has a 22,000 mile surface area. So what this turns out to is actually about a 16th of an inch of water on the ground. It's a sheen of water. Okay? So that's 2.2 trillion computations per second in 2000. So you think this is ridiculous. We've been at it for 60 years. This is not going anywhere, right? But suddenly, right, as soon as you think nothing's going to happen, by 2020 you have 40 feet of water. By 2025 you're done. So after 60 years, 70 years of waiting, nothing's happening. You've just been following this trajectory. By 2025 you've achieved the compute capacity in a single sort of tissue box sized computer of the human brain. So this is actually happening. No one could have imagined that we would have this magic oracle system that you can talk to, can answer any question that you want, which is exactly what Google is. Our grandparents couldn't have seen that coming. This is a likely outcome if things keep going the way they are. So what's the end state? The end goal here is utopia. Nothing short, right? And I'm starting here because I think it's important for as many people as possible to understand that big picture. We can build product with machine learning, but the real goal here is like deliverance for our species, right? This magic system that can answer our questions, solve our problems. This is totally conceivable. We think of ourselves as being at the top of the intelligence hierarchy. We're probably somewhere at the bottom of it. There's way more room above us. But before we get there, there's a lot of tricky issues to navigate, lots of ethics problems to solve, lots of laws to write. You guys are going to be our future sort of business leaders, so that's why I'm here. I want you to all feel comfortable thinking about machine learning, and I think this is how it starts, with kind of getting our hands dirty. And I also don't want people to be able to trick you by talking about deep learning and machine learning. And I see a lot of that, so that's kind of why we're doing this. All right, let's get into some actual material. Okay, so this is a data set. This is what data sets in the real world look like. And we have a bunch of different kinds of data in this data set, a bunch of different kinds of columns. We'll kind of go through these. So this is supposed to represent email data. The first column here is email ID. It's a numerical field. It's just a number. Maybe it's a unique number for every email. Makes sense? And you can imagine when I say data set, this is a CSV file on your computer or an Excel file, like an Excel spreadsheet, just a table on your computer. Another column here is subject, which is a text field, just text data. Sender IP, another text field. But you and I know that these are different kinds of text fields, right? We know that the information in this is different from the information in this. It's not just both text. But as far as the computer knows, it's just text. A categorical field, account category, account country rather. So a categorical field is a field where you can imagine that in the product or wherever this is coming from, it's a drop-down. So it's just a bunch of categories, right? So it's a categorical variable. And remember, the variable is just a number. So you have a number of recipients of that email. These are integers rather than numbers that have decimal points. And then a datetime field, which is just a date represented in a way that a computer can read, and that also we can read. But it's sort of consistent throughout. We don't use MAR, we use 03 for March. And then the last column here is spam, which is a Boolean field. Boolean is true, false. Yeah? So you can imagine this data set representing what we know about emails and which ones might be spam. Does that make sense? So we're going to keep jumping back to this slide because the idea is to talk through a machine learning pipeline with this slide as an example. Okay, so some terminology. So these are terms that you'll hear very often. The first set of terms, supervised versus unsupervised learning. The question, so the thing that determines whether you need to do supervised learning or whether you have to do unsupervised learning is whether or not you have labels. Well, what are labels? Well, in this data set, what would be a useful thing to know? Well, based on what I'm showing you here, clearly the idea is that we want to build maybe a spam classifier, something that can tell what is spam. And so if that is a task we want to solve, that column is a label. Someone went in somewhere and said, this email was not spam, and this email was spam. So a human used information in their brain to provide labels. Yeah? So we want to train a system to pull the information out of this so that it can make predictions on its own. That's the idea. If we have that column, it is supervised learning. And if we don't have that column, it's unsupervised learning. So you might say, what does that even mean? If you don't have the thing that you're trying to predict, what are you learning? Right? So say you didn't have that column, so you just had this stuff over here, these 1, 2, 3, 4, 5, everything besides is spam, up through send time. If I just gave you that, a smart human could look at this and be like, oh, that looks like spam. Right? There's structure in this data, without even providing a label, there's structure in this data that can be exploited, certainly by a human who has all this world knowledge about what all these words mean, what IP addresses are, etc. An arbitrary machine learning model won't, but it can still learn structure in data, even if you don't have labels. But we're not going to be doing much unsupervised learning today at all. We're going to be doing supervised learning, which is what you're going to see a lot more of in sort of production contexts. The next thing you'll hear about a lot is regression versus classification. So what does this mean? This just means, this is just referring to what kind of label you have. That's it. So in our data set, this column here, it has two possible values. It's a Boolean field, but it is equivalently two categories. One category is that it is spam, one category that it's not spam. So this is a categorical variable. Rather than a numerical variable, which is a number that you might be trying to predict. If it's a number, you're doing a regression task. If it's a class, you're trying to predict which of several classes this example falls into. It's a classification problem. Cool. Okay, so this is what we're going to be doing. This is sort of this is how every machine learning pipeline works. You have some table, you split your data. Step one is you split your data into training and test sets. Well, what does that mean? So say so in this data set, we have 1, 2, 3, 4 samples, and 1, 2, 3, 4, 5, 6 features. Feature just means column, and samples just means row, more or less. So what we would do is choose some rows to put in one data set, and some other rows to put in another data set that we do not show the computer. Okay? So we'll say, I don't know, let's just cut it over here. And we're going to take these rows and we'll call it our training set. And we'll take these rows and we'll call it our test set. So that's step one, splitting it into training and test sets. Step two is feature engineering. Now there's no quick way to describe what feature engineering is, but the bottom line is, whatever you're feeding into your machine learning model ultimately has to be a vector. It's a vector, it's a bunch of numbers in a list, in a certain order. You can't change the order. You can conceptualize it as an arrow, and I'll talk about that intuition a little bit in a little while. But every single piece of information that goes in has to be turned into a vector. So how do you turn Q1 goals catch up into a vector? Right? How do you turn USA versus AUS into a vector? We'll see how that's done. So that's feature engineering. The next step is selecting a model architecture. What does that mean? That means picking some function that you think could be useful for predicting your label. And there's a set of functions that people have found through trial and error over the last 70 years that are useful for this stuff, and that's what machine learning is. But the space of all functions is your set of options, and you're just going to pick a function, and then you're going to have some parameters in it that you have to fit. So this might just all sound like words right now. I'm giving you a high level. We're going to do all this in a moment. So selecting model architecture means that I'm going to pick some way of combining vectors and parameters to get an answer. And then training the model means figuring out what the best value of those parameters is. So what does that mean? I'm going to do a really quick example on board. Maybe I'll just do it over here. So with a linear model, what you're doing, so say you were looking at this table over here with a bunch of columns, right? So say you only had two features, x1 and x2, and you had two samples, whatever, sample 1 and sample 2. And the values, and the only data you have is, this is a sort of synthetic problem, is just, these numbers feeding into, say this is your data set. It's a completely theoretical thing. Say you were to decide that you wanted to use a linear model to fit this data. What you'd be saying is that you think that there is some vector theta that can be multiplied by each row here to get an answer. Okay? So that means, and so what is theta? It's two numbers. And you want to know what values of A and B, when multiplied by this sample, give you some number that is equal to your label. So you had some label, this is a supervised problem. This is your label, your ideal label, and it has some values 2, 5. So what you're going to do is try to find the A and B such that A times 0 plus B times 1 equals 2. A times 0 plus B times 1 equals 2. And A times 1 plus B times 0 equals 5. That's what fitting parameters means. It's finding the A and B such that this is true. This is for a linear model. We'll do it with a bunch of models. If that doesn't make sense, if that's okay, we'll go through it more in a second. Hope that sentence doesn't become a theme. Cool. So I think we're going to stop there, and we're probably going to go into the notebook. Because the rest of this is a little bit theoretical. We're going to skip it. Okay, so what I'm looking at here is, you should all be able to see on your screens as well. Can you raise your hand if you cannot see this on your screen somewhere? You can also see it up here. That's loaded, okay. So I'm going to be typing stuff here, and I invite you all to type along in your own Colab notebook. Feel free also to take a break if you feel like it's going too fast or just getting tired of typing. That's okay. But obviously the idea is to type along because that's the best way to learn stuff. And we have TAs here who can help. I can help. Feel free to raise your hand with questions if you have. So I don't know, has everyone gone through this stuff as well? Have you downloaded this file and uploaded it again? No, you have not done that. Okay. So if you haven't done that, please go to this URL. This is kind of not the optimal thing, I apologize, but please go to this URL. You're not going to need this data for a while, so it's good to just get it started now. You just open this URL in a new tab, and it's going to ask you to download a file. It's going to be Sloan ML datasets.zip, I think, or data.zip. And then you're going to type out this. After you've downloaded that file, and hit Shift-Enter after you type this out. And when you do that, you're going to get this little box that says Choose Files. I'm going to click it, and I'm going to pick the file that I want to upload, which was my data.zip. And then once that's uploaded, there's some lines here for this will unpack that zip file. This is going to move everything inside the folder that it created to your current directory. So you don't have to do this now, we can do this later. But what we're going to start with is, let's see here. What am I doing here? So I'll explain it in a second. Okay, I've done a bunch of stuff that may not be familiar. You are looking at Google Colab. This is an environment released by Google to make it really, really easy to write Python code in your browser and execute it in a virtual machine, in a server class, in a data center somewhere in Montreal, or Virginia, or whatever, right? It's pretty amazing because, so every time you type something into one of these cells, you're writing Python code, and every time you hit Shift-Enter, you're running a Python program. If you hit Enter, you're just going to insert a new line. If you hit Shift-Enter, you're going to run Python. So you'll see there's a bunch of colors also on the screen suddenly. What's going on? Okay, so these, huh?
Just zoom in.
Yes, absolutely. How's that?
This is good. Yeah.
Thank you. So this stuff, if you haven't done it already, that's fine. We'll get back to this when it's actually time to start working with data. We're going to start with Python first. So this is Python code that we're typing in these cells. Every time I type a number sign like this, I'm typing out what is called a comment. A comment is something that is not actually executed Python code. It's just something that you write down to indicate to other programmers what is going on. So you'll use them to explain what you're doing, basically. So if you don't want to write what I'm writing in comments, you don't have to. It's not going to affect the outcome of your code, but I'll be including them so that you know what I'm doing and you can keep track of where we've been.
Yeah.
Yes?
Just not worry about the file download right now. I was trying to download it and it's not, I'm not at the same place, but if I don't need it, should I just ignore it and watch you what you're doing?
Good. It's good to definitely download it and upload it, because that will take whatever, a few minutes, and it's better to not wait for that later. So yeah, it's just good to get this file downloaded on your computer, and then run this code. Hit Shift Enter, hit Choose Files, and then choose that file.
Go do that step one more time.
Yep. So I'm opening this in a new tab. It's gonna, oops, not this. I'm gonna download the file up here. It's gonna get downloaded, and then I'm gonna do from google.colab import files, files.upload, open parenthesis, close parenthesis, Shift Enter. Choose files. Data.zip. And then open. And then you're going to see this little bar.
Do they have to unzip first?
Nope. So you're going to see this little thing. It says 1%, 2%. I've already uploaded it, so it's uploading it to data1.zip because I already have a data.zip.
Yeah, all of that.
He's been doing it for a while.
How are we feeling? Yep.
I keep getting an error message when I try to upload.
Yes.
Do you need a separate notebook to?
Do you need
To establish a separate notebook to continue writing code here, or?
do you need a separate notebook?
Yeah.
You should be using your own notebook. A blank notebook with nothing in it. It's going to look like, like this,
Yes.
with
It
nothing.
says avocado.
And the idea is whatever you're seeing, you type on your own and run it on your own.
But I mean, like separate notebook from uploading the data set versus the rest of the stuff.
Oh, no, same notebook. Just one notebook all day. Whole day, one notebook.
We have like not data zip, but like
Oh, sorry, did I get the name wrong? What is it called?
slow-ml/datasets.zip.
Okay. Sorry, guys.
Why don't we try to pick a new topic?
You got a lot of talent.
Yeah, so you're supposed to have one. Okay, let it be.
So it's 10:36 and wait till 10:40. Hopefully we can figure this out by then and I'm going to proceed. Is that everybody else? Or raise your hand if you've already downloaded it and uploaded the file. Okay, I'm going to give it 2 minutes. Yeah, it's because I'm stupid. And so that's the So basically, what happened is I thought the file was named data. That's it. That's it. So you're just going to put that correct name here.
Well, just unzip the file and then upload that. Even if it's 3 out of my 5.
Hey. This is
Yeah, so it's like, I was you know what?
Yeah, no, I typed it wrong and I fixed it after some position. Yeah, it's right. Okay, so when you
It is getting a message
Don't
that
do this.
okay, that's sample data. So one more dumb thing I did. Oh wait, no, that's not. You didn't You didn't, so it's just unzip it.
I think not everyone's having that issue, so you want to just
Just gonna-
maybe.
Great job. Okay, so now you I'm just gonna move it inside data. Oh, is that
And then it calls
everything? I just said yes. You're opening the file on your laptop. What you want to do is upload the file, and then you're going to choose data.zip. Can you go over and no, you click this. Now you're going to Sorry? You doing Chrome?
If anyone
I mean, it's
using
gonna
a
be a
different
file.
browser other than Chrome, this might not work. So please use Chrome for this because this is in the Google environment. Some people are not using Chrome and it's not working for them.
You know what's happening?
I think in Safari it's just unzipping files.
Yes, okay, so that I just saw it.
Yeah.
Wherever it downloads the zip file is also where it unpacks it, so you can just find data.zip in that folder and upload it. Or just use Chrome, which doesn't do things you don't ask it to.
So
That's fine. That's fine. You're gonna have a lot of stuff. Which we just pointed out, you can also just upload all those CSV files on their own. That's fine. Just upload them. File that upload, pick them all. Real world engineering issues, right? So it begins. That's going to be a theme. I did a little bit of cleaning with the data that I uploaded for you guys, but not a whole lot, and I think that's good, because you're going to run into problems, and that's like what happens in real life. I think that's enough waiting. Raise your hands if you've uploaded the data, or if you feel like you can at this point. Yep, that's it. Great. Okay, I think we're going to move on. Cool. So welcome to the Colab environment. Told you guys about how you're executing Python in each of these cells. You can either hit Shift-Enter to run the cell, or you can hit this play button. The play button turns into a stop button when it's running, and you can always stop the computation. So what we're going to start with is what you always start with when you're learning a new programming language, which is Hello World. The goal of which is to write a program that will just print out the phrase Hello World. The way we do this is with print hello. Fantastic. So we hit Shift Enter and it executed, and it gave us a new cell to work with. What you'll probably want to become comfortable with is keyboard shortcuts. You're moving around in Colab a lot. So you can go to Tools, Keyboard Shortcuts to take a look at what they are right now. There's a lot. But the main ones that you want to know are creating a new cell below where you are, which is by default on Macs. I don't know what it is on Windows. I think just Control instead of Command. But it's Command-M-B for opening a cell below, and Command-M-A for opening a cell above. Just makes your life a little easier. Or you can mouse over here and click Code for a code cell or Text for a text cell. You can mouse over in any divider. And then Command-M-D to delete a cell if you don't like what you're doing. You can also just, delete it like this. So moving on. So what's going on here? We see a bunch of colors already. This is called syntax highlighting, and it refers to the fact that this environment is coloring different words based on what they do. Python doesn't care what color the words are. We're not coloring the words. The UI is coloring them for us based on what they do. It's turning functions blue, and it's turning this thing over here, which is a string, which is the computer science name for words or characters, it's showing that in red. And it's showing comments in orange. Okay? So you just wrote and ran your first Python program. Congratulations. And there's also a few ideas you got access to here. So this is a function, which is a thing that you can pass something into, so that it can perform some unit of computation, either give you an answer back or do something. And so print just prints. We're going to go now through a bunch of, really quickly, basic stuff. So maybe I'll start with a little section here called operators. What are operators? They let you perform, well, you'll see in a second. Plus is an operator, so addition is just that, as you might expect. And multiplication uses asterisks, like this. So I'm just doing shift enter every time. And again, remember, you don't have to type the comments if you don't want. Division is just a forward slash like that. If you can't remember the difference between forward and backslash, which is an important distinction, imagine that it's standing and it's leaning forward versus it's leaning back. Right? So this is leaning forward, forward slash. Always use forward slashes for paths, like where where a file is on your computer. It's a path. And so look at what came out here. It's a different output from this. Right? There's a .0 here. That's because there are different kinds of information in the computer. The 15 is an integer, which means the computer doesn't want to retain any information for what's smaller than 0 component, smaller than 1 component. And then here it's a float, where it's actually keeping memory aside to store the point 0 and to remember that it's 0. So it's different inside the computer. And then a slightly different operation, floor division, which is just, hey, just do a division and give me the round down the answer to the nearest integer. Just sometimes useful. Another operation, modulo arithmetic. So what is this? There's so many words, right? There's all these words for things. They're all very simple concepts. What is this? Modulo arithmetic is tell me what the remainder is. So 12 modulo 5 is please divide 12 by 5, which goes in 2 times evenly and leaves over 2. So it's going to say 2. Or maybe if this is unclear, let's do 7. Sorry, not flood division, floor division. 7 divided by 5 goes in once evenly, and then modulo remainder 2. So that's another operator. Exponentiation is 2 asterisks. This is going to be 27. And then you can also take square roots in a similar way. You could do this. So square root of 3 is also 3 to the half power. Or you could use a function that is built into Python. So we're going to do something now. It's very important. We're going to import a standard library module. The way we do that is by typing import and the thing that we want to import. There's a lot of stuff you can import. It's a very large space of options. And anyone can write anything that anyone can import. And anyone can install it. So the value for using the Python ecosystem comes from all of these things people have built in Python that you can just import and use very easily that bundle up complex computations and lots of work that you don't have to do. So we're going to import math. I didn't hit shift enter here, enter. So I'm typing 2 expressions in one cell. And I'm going to compute the square root of 16. Another thing happened here. There's a dot in here. What is this? So math is a bunch of code someone wrote, and it has a bunch of functions in it. One of the functions in it is called sqrt, which is square root. And you just pass it a number, and the way that it works is it spits out square root. So what stuff can you import, and what stuff is inside stuff? How do you know? Well, in normal Python, if you're just writing in a text file, you wouldn't be able, you'd have to go look on the internet for what is inside math. What other libraries are there? But because we're in Colab, which is amazing, what you can do is type import space, and then just hit tab. Okay? And this is everything you can import. And there's a lot. And if it takes a second to come up, it might be because you're not connected to a runtime. It'll ask you to connect to a runtime or a kernel, and you'll do that, and it'll work. And then another question you might ask is, what is the set of all things inside stuff? So to do that, you can, again, do math dot and hit tab. And it'll show you everything. And another thing you can do, say you don't know how something works, we're going to type out one of the functions in there. We're going to hit question mark at the end, and then run this cell. So shift enter. Boom. Return the square root of x. And it tells you how it works. And of course, Google is your friend in all things. You're going to have to run into tons of errors. Just Google them. Learning to read errors is a bit of an art. But anyway, we'll come across that. And the final thing I want to cover with math is grouping and PEMDAS. So this is different from this, right? We want to use that fact. So we'll use parentheses to sort of group expressions. Great, so you guys now understand operators. Now it's time to talk about variables and primitive types. How you feeling so far? Yeah?
How do you click run?
Shift enter. Yes?
One question, do spaces matter when you're...
Great question. Fantastic question. Okay, I forgot to mention this. Sometimes spaces matter, sometimes they don't. How do you know? Do what I do. So I'm writing idiomatic Python. What that means is I'm writing Python the way that people write it in the real world, and if you copy that, you're going to be in good shape. If you don't put spaces here, this will still execute, right? So Python doesn't care about these particular spaces. Sometimes it does, and you'll learn where, but it doesn't care about these ones this runs, right? But the world has decided this is uglier to look at if you're an engineer looking at massive volumes of code. And so there's just sort of style rules everyone's agreed on, and you should probably try to follow them. Because if you're ever writing Python, you want to write it the way people write it, and not in a weird way. So try to copy where I'm putting spaces, and I'm going to try to be idiomatic about that stuff. Any other questions? Yes?
Once you import like is it called a library
Yes.
for that notebook? Do you need to import it again every time you try to write something? Or?
No. Another great question. So this notebook is running on a virtual machine that you control the entirety of, and it's going to be alive until you close your tab. If you close your tab, everything that it has in RAM gets deleted, but that's fine because everything that's stored on disk stays, and you can just run all your code again, rebuild all these variables, and whatever else you want to do. Maybe that didn't make sense. It'll make sense in a moment. Well, I'll show you now, actually. Math will be around for the rest of the day. Because we didn't import math. So that module will be around for the rest of the day. And it'll be called math for the rest of the day. But you can, if you were to, let's say, I don't know how I close the runtime. Tools. Oh, restart runtime, right? So if I restarted runtime, we would lose all that information.
I meant if you so say you imported a different library,
Uh-huh.
Can you still run math functions?
Yes.
Okay.
Yes. We're going to import many at a time, and we're going to use them all. Okay, variables and primitive types. What's a variable? It's a thing that you put information into. And what is a type? Well, we already saw when I had that data set up on the screen, there's different kinds of information that get stored differently in a computer. So that's just what a type is. You have to pass functions the kind of information they expect, otherwise they're not going to work. So what kinds of data are there? So Boolean variables we already saw. And we're going to assign, so this is the first time we're seeing this, we're going to assign the value false into the variable data. So now data has the value false. I hit Shift Enter. I didn't print anything, but I can type out data and then hit Shift Enter and it'll tell me, hey, that's false. And I can also do, hey, what's the type of data? And it'll tell me that. It's a Boolean. Other types of data, integers. So now data takes the value 3. So I assigned 3 to data. What I just did here is that I overwrote this previous value. I cannot get that back. Okay? The only way to get data to be equal to that again is to run this cell. Because the state inside this machine has changed. Data is now 3. It does not remember that it used to be false. Make sense? Integers, floating point operations, floating point numbers. Floats. What is this? This is just numbers with decimals. Type float. And then strings. We can use double or single quotes. So now data is some string. You could also have done single quotes. Also, I did this underscore for the spaces, it could be whatever. And now data is a string. And now let's talk about some logic. So we know what equals does. 1 equals sign says, please put the thing on the right-hand side into the thing on the left-hand side. 2 equal signs is something completely different. Okay? 2 equal signs is, tell me if the thing on the left-hand side is equal to the thing on the right-hand side. So I'm not storing 2 into 1. That doesn't make any sense. You can't put a number in a number. It would complain if I tried to do this. 1 equal sign. Can't assign to a number. That's ridiculous. Can't assign to a literal. But if I do this, it's telling me, no, 1 is not equal to 2. So that's a logical operation. And they're very different things. You're trying to put information inside a variable with 2 equal signs. That's not what you're doing. You're seeing if the variable is equal to the thing on the right-hand side. So that's basic logic. You can also do this with comparators. So is 5 greater than 3? Yes, it is. Is 5 greater than 3? And is 5 greater than 2? Yes, it is. Is 5 less than 3? Or is 5 greater than 3? Which is obviously going to be true. You can also do stuff like this. What's the inversion of that whole thing? If that was true, this is going to be false. Does that make sense? So this was logical operations, comparison operator. This is conjunctive operator, logical operator. See how all these words, right? It's just and. This is what you're going to find it described as in books. And that's annoying. Because the concepts are pretty simple. Okay, great. Making good time here. How's everyone doing? Great.
How do you create the new code?
So you can either hit this thing up here, plus code, this little add code cell, or you can mouse over any of these white gaps between cells. You see this little gray line appears, and you can just click on code. Or you can do Command M B to open a cell below, or Command M A to open a cell above. And you can change those all up here. Let's take this out. Cool. Next step here is, okay, we're going to learn about more complex types of stuff. So we learned about integers, floats, strings, all this stuff. More complex type, lists. So what is a list? Just a bunch of stuff in a certain order, stays in that order, and you just kind of keep it in a variable. What does that look like? They use square brackets. Boom. That's all it is. You can put whatever you want in there. You can make it strings. That's all fine. You can also make mixed types. What we probably want to do is run some computation on every element of this array, of this list. And so if your list was this, you would need to write the function that you're running on each element to be able to handle both integers and strings. So you might do this, but in practice, you're going to have a bunch of the same kind of thing inside some list. So this is mixed types. Single types. Indexing. So if you want to get something out of a list, you can use, again, square brackets. So you define it with square brackets, and you can do stuff like this. So if I want to take the first element of a list, I put in the number 0 here, which is a little unintuitive. And that's because the first item of the list, so let's make this a better list. Let's make this like that. This is going to print A. So A is actually the 0th item of this list. The way that we describe this is that we say Python is 0 indexed. So the first element of the list is B, the number 1 element. The number 2 element is C, 3 element is D. I can also do, hey, what's the length of data? It's 4. If I want the last element of data, I can take its length, which is 4, subtract 1 from it, and take that element, if I didn't know how long data was. But I know how long it is, so I can just take the 0, 1, 2, 3 element, and I will get D out. Another thing I can do is, if I don't want to type 3, I can also index backwards. So if I do -1, it's going to take the first item from the end. So 0 is always this one, but -1 is this one, and -2 is this one. The data -1 is going to be the last item. And so this is negative indexing. And we're going to learn about ranges. So I can also take a bunch of data. I can say, show me from the 0th item through the index 3. So this is 0, 1, 2, 3. What it's going to do is spit out 0, 1, and 2 when I type it like this. If I want all of it, I'd have to do that, or obviously just data. Or alternatively, not range x, ranges. Just a colon in the middle also works, it's the whole list. But that's how colons work inside square brackets when you're indexing stuff in lists. Is this tracking? Raise your hand if you're like super confused. No one's going to do that. I'm confused.
We had someone, yeah.
Yes.
Can you explain the last one where you just put the colon and it popped up with everything else?
This is shorthand for take every element of the list, because I could have passed specific numbers here, and it's going to say take from the 0th through the 3rd. But if I drop them out, it just assumes I want all of it. But you're never going to do that. You're just going to like get the list.
And why do we have A, B, C in quotes?
They're all strings, and I define them. I define it that way up here.
Okay.
If I had put other stuff in here, like integers, they would have not had quotes around them. So there's a so Python is showing you that they're strings by when it returns them, putting them in quotes. But internally, it knows this is a string. Great. So we can add stuff to lists like this. I'm going to speed up a little bit. Well, probably better to optimize for comprehension. And so we added E to data, and now E's in it. So if you recall, this is, again, we did dot function before with math. This is another dot function. So maybe you didn't know, how come, data was a list. I can dot stuff on a list. You can't. There's methods on every object. So when there's a function attached to an object, like a list or a string or whatever, it's called a method. But it's just a function. Yes?
A question, -1, if you put it in the brackets, will always call the last part of the string, of the array?
This is the last element of the list every time. Cool. So one thing worth knowing about is we can also delete variables. So if I want to get rid of this completely, I can just do that, and now it's gone. If I try to print it now, Python complains. Because it's gone. But I can always reassign it up here by running this cell, and then I can come back down here and run this cell, and it'll work. Cool. Lists, done. Dictionaries, another very simple data structure. So lists is just store a bunch of stuff. Dictionary is store a map of stuff, so curly brackets. So what is this? This is saying, I want you to associate the key A with the value 1 and the key B with the value 2. And I can ask this object for the value for some key. You can store maps of information like this. And I can also change stuff in there, so I can say, I want you to add 1 to the value that's in there. And now data A is going to be 2. And I can get a list of everything that's in this object just by doing that. Just the values. Just these two guys. Or just the keys. And if you're ever wondering, what else is in here, remember you can always just do .tab. See everything you can do with it. Or you could do that. And it'll tell you everything about dictionaries. Or you can just Google it. Cool. Dictionary is done. Control flow. What does this mean? This means telling our program how to make decisions based on the values of variables or other things that it needs to consider. So the first thing we're going to see is if and else statements. So say I have some variable, and I assign it the value 5. And now I want to do some logic with it. So I can say, hey, if the value of the variable is over 5, colon, enter. Well, what just happened? It just put in spaces for me. Why did it do that? These spaces matter. So if you write if statements, other kinds of statements we'll see, the degree to which you indent the line below it tells it when the statement is done. So you have to have these two spaces here. You can also do 4. 4 is very common. Google does 2 by default in Colab. You can change that setting. It doesn't matter what it is. You have to have spaces. 4 is very common. You can change the setting in here somewhere, but that's not relevant. So we're just going to leave it at 2. So we're going to say if the value of that variable is bigger than 5, print bigger than 5. Is it? It's not. Great. Or we could also do something like this. Right? So this is going to print a different thing when we change the value of this variable so that this if statement is false. Or we can also add this other thing that checks another condition. That just happened. So if the variable is bigger than 5, print bigger than 5. Else, if, this is called else if, or elif, else if the variable is exactly equal to 5, print exactly 5. Otherwise, say it's not bigger than 5. This is going to say not bigger than 5. If I change it to 5, it's going to say exactly 5. Basic control flow. Another kind of control flow is for loops. How are we doing on time? 11. Okay. This is going to say, go through this list and print the items in that list one by one. So we're iterating over a list with a for loop. And inside that loop, we're executing this function. And as soon as the indentation changes or the cell ends, the end of the for loop has been reached. Yes?
What's the shortcut for opening a new coding box? Or
I've been using Command B. Command N, and then B. And then another kind of, so another kind of loop is a while loop. So say we had some variable that we set to 0. We could say, as long as the variable is smaller than 10, add 1 to the variable and print its value. So this stops running as soon as data is 10. It's updating its value inside the while loop. We are done with control flow. This is our final Python section before we start machine learning. And that is functions. Oops, I want a text cell. So we use the word def to create functions, or the keyword def, I should say. So when we do that is we write def, then the name of what we want the function to be called. And we type an open parenthesis to indicate that we can put stuff into that function. We can put as many things as we want into a function. Here, this function is taking exactly one argument. Argument is a word that for something you put into a function. I'm just going to write these down. And inside of this function, we're going to write the code for what it does. So the formula for this happens to be this. So there's a return here. This tells Python that this is the thing that I want you to return to the user, to the caller of the function, when they call it. You have to have a return at the end if you want it to spit something out. Otherwise, it won't spit anything out. It'll just do stuff. So I can call this function. Great, as expected. Excellent. Yes?
How many returns can I have in one function?
How many return? Only one return. As soon as in function execution, Python sees a return statement, it leaves the function. So anything down here is irrelevant. This is never going to get run. Great, so we understand functions now. And maybe one more thing I can show. If I want to test that this function does what it's supposed to do, I could write this. So writing tests is a good habit to get into so that you know that your code is doing what it should. So I can say to it that we need this to be the case. So if I run this, it's going to be true, and it'll just work. Nothing happens. But if I tell it I want this to return 212.1, it's going to fail. We're asking Python to let us know if this function is not doing what it's supposed to do. Great. We are done with basic Python. So what we're going to get into now is an intro to machine learning. How are we feeling? It's 11:10. Do we need like a 5-minute break? Or is everything okay? Yes?
Just one question. I think it was line 76 or something. The data equals 0 while data is less than 10.
Yep.
What do you use that for?
So a while loop is something that you'll use. Good question. And maybe I'm not explaining when you'll use stuff often enough. So a while loop you use when you don't necessarily know when you're going to stop running. You just want this thing to keep running until some condition is met, and that condition can be anything. So you could even do something like, let's see. You could do while true, print A. Now what's going to happen when I run this? This is going to run forever. And it's just going to spam the UI. Okay, it's just going to go forever. And I don't want that, so I'm going to stop execution. But I could also put something here that eventually evaluates the false. And then it'll stop. So say I want to, like, a web server will often have a while true in it. You want the web server to just be up. And it just never stops. It's, it's kind of forever. That's one implementation. Cool. So in terms of break, do we need time? Should we just keep pushing?
Push.
Maybe
5 minutes? Okay, cool. It's 11:10. We'll resume at 11:15.
If anyone is yet to check in with logo, please do that so you can get your refund. And also we have a hashtag for the event. He's writing it down right now. Feel free to use it. Yeah. He's writing it down right now.
I'm just going to check.
Just like, join them there, and like now they're on break. You can walk the room like the PA, so like ask if anyone needs help. Just walk the room, go table by table.
So they create a break?
Not yet. They will not yet, but just like they're just like uploading things.
Yes.
So this is going to kill your time.
Yeah, a little. I feel like mostly yeah, but I never knew.
I don't have
Does anybody have any questions?
Good.
How you doing, man? Heading from it's good to keep that This is fun. Yeah. I feel like are you doing okay? I use other I do syntax. I use
Yeah, like it's a lot of fun. Exactly. It's when the two teams are like, we got like we all got one together. And I think that's Saturday morning. It was fun, but I think after a little bit we had. No, it's not. I know how hard it is, and I feel like
All right. So one question that came up over the break. One question that came up over the break, which is a very good question, is why are we using Python? Because it's the best. Objective. So the ecosystem. So every company on Earth that's doing even the most cutting-edge machine learning research is using Python. If you're using it in production at companies, you can use Python. If you're 5 years old and starting to learn how to write code, you can use Python. So it's an extremely versatile language, extremely powerful, with an extremely robust ecosystem. It's built on top of other stuff that is very fast. So it's not slow. It's just as fast as everything else. And it's super easy to write. So this is basically the easiest that programming has ever been, right? Open your browser and just type almost English, more or less, right? This looks nothing like C. C is horrendous, Java is horrendous. All these other languages are horrendous to actually write stuff in, experientially. They give you better safety and security and more sort of stability in production environments, but you can do everything in Python. HubSpot uses Python in production all the time. So Python's amazing. We're going to import a bunch of libraries soon that we're going to use very heavily that make our lives very easy. And that's only true in Python because of the ecosystem. Yes?
How would you compare to R?
Good question. So R is older, kind of more common in the statistics community. It does not have anywhere close to the kind of horsepower that Python has now. Not like orders of magnitude behind. Starting like 3 years ago, more than 6 years ago. Because you have Google, Facebook using TensorFlow and Torch built on top of CUDA, built on top of NVIDIA stuff. It's this whole stack that works seamlessly together, and no one's done that stuff for R. Or maybe they have, but it's like, here and there, not a cohesive, integrated ecosystem. So a lot of what we're doing in this section, you can absolutely do everything you can do in R. The last section, hopefully we can get to it, the deep learning stuff, that you're not going to be able to do that on GPU. And I don't know any native R, R GPU ops stuff. Maybe it exists. Any more questions? Yes.
Why not Julia?
Julia's great. Julia's great. Julia's a really good language. It's beautiful. I also like Mathematica a lot. There's a lot of languages that are beautiful and good for sort of scientific computation and stuff. But I think if you want to do machine learning research or deep learning at all, you kind of have to stick with Python. That's kind of the obvious natural choice. Although there is good numerical computing stuff for Julia now as well. So that's not, it's not a bad option. Ultimately, it's a matter of ecosystem, right? You can learn the syntax, but the real benefit is what work have other people done that you do not have to do, right? That's why Python's amazing, because other people have done a huge amount of work, which we'll benefit from in a moment. Starting now, in fact. So we're going to import some libraries. I'm going to import 3 libraries. They're going to seem a little alien, but you're going to see these 3 libraries all over machine learning code on the internet. The first is NumPy. NumPy is used for numerical computing, and it basically allows you to do fast vector and matrix stuff. Under the hood, it's all C, so it's very fast. And what we do usually is we don't import NumPy just as NumPy as it is. We give it a little nickname so that we can refer to it as a short form. And the nickname we're using is NP. And this is idiomatic. It could be anything. And later we can call whatever dot functions inside NumPy, right? Python doesn't care what we name it. But I'm going to name it NumPy because this is what everyone does. It's arbitrary, but it's universal. So you're going to see literally import NumPy as NP in all kinds of code. We're also going to import another library called Pandas. Pandas helps us with data manipulation, dealing with data sets. And the last one we're going to import is scikit-learn. This one's not going to get a nickname, it's going to be scikit-learn. And so this is how everyone will always do it. We'll import pandas as PD. Again, it could have been anything. We kind of all just agreed to do these things these ways. So I'm just going to run this, and they all imported, and we're done. We're not going to see any output. So you should have all hopefully downloaded the data. Now's the step when we start accessing it. Make a whole section here. So if you could all just type !LS and then shift enter, you should see a bunch of stuff in here. If you see a file called telco-customer-churn.csv, you're set. You see a telco-customer-churn.csv. Raise your hand if you don't. Okay, do you see data?
You see the file name?
You don't see data?
Sample
Stable
underscore
data.
data.
But you don't see a data? That means it didn't upload. We're not gonna, we can't do anything, we get this figured out, so let's give this a few more minutes. If you don't see a data.zip, can you raise your hand if you don't have either telco, churn, whatever, or...
He doesn't see it.
Okay.
But I'm looking for internet telecom.
I'm just going to upload that one file in a separate location, and anyone who's having trouble can just download that one file.
This is it.
Telco customer.
Start by the first part.
Yeah.
Now before we look at this. You can. Did you try it anymore?
And then I'll write what we want.
Well, that's just the case.
All right, so I put the file at a new path, just the telco file. That path is tinyurl.com/sloan-ml-data, so I'm going to put that in here. So what you're going to do, hopefully this works. Or actually, sorry, you're not going to do this. You're going to here. Download this guy.
We just need the tree.
This URL right here. Download that file from Google.Colab import files.upload, open, close, shift enter, choose files, and then
Yes, I didn't. Basically, my download was zipped, so I unzipped it. Yeah, I mean, I did not.
Raise your hand if you're still having data issues. Okay.
Run the upload.
You got it.
Yeah, so you unzip one. And then you can scroll back. Get the function at the very top from Google.
Give it another minute.
Rerun that function and when you choose file.
Now, if you go into this, unzip that. Then when you do this,
How you doing?
if you don't specify
Oh, they didn't do it. But they have it.
Where was this from? I don't remember.
Okay. It seems like a lot of people are caught up. Raise your hand if you can move forward. Cool. Awesome. So we have this file, telco customer churn.csv. When we run ls. So what is this exclamation mark? Colab and also the thing that it's built on, which is called Jupyter, are really cool because what they let you do is they let you run not just Python, but they let you actually run commands on the computer that your Python is running on. And you do that by using exclamation mark. So this ls is not a Python command, it's a Linux command, and we're running it in Linux inside a virtual machine in the cloud. And it's telling us to list all files in the current folder. And it's listing them, and one of them is hopefully telco customer churn.csv. Cool? Cool. And you can do a bunch of stuff after command. So if you want to learn Linux, and just as an aside, you don't want to do any work to like set up a Linux environment, you can do it here. So you can just do any, what folder am I in, and it just tells you this is on some virtual machine in the cloud. Anyway, cool. We have our file. Let's load it up. So we're going to write down our file name, just like this. Put it in a variable. And what we're going to do is use a method inside pandas called readCSV, which reads CSVs. You don't have to do any work. And what it does is it spits out an object called a data frame, which is basically just a wrapper around the information in that CSV. So how do we do that? Data frame equals pandas dot read CSV, oops, lowercase, with an underscore. This doesn't matter. File name. Done. So now df contains a data frame with all of the information that was inside telco customer churn.csv. How do we see what it contains? We can ask it what columns are in it with df.columns. Cool? So okay, a bunch of columns in here. Let's see what the data actually looks like. We can run .head on the method head on the data frame, and it'll spit out the top 5 rows of the data frame. So we're seeing here, okay, it's all this data, bunch of columns, 21 columns. Yes?
Sorry, I'm getting module pandas has an attribute read underscore system.
Did you try just reloading your that's usually what it is. Sometimes the runtime disconnects and it loses track of where the libraries are. If you just reload, so you're going to reload the page, refresh literally, and then just make sure you run the cell that says import pandas, because as soon as you reload, nothing's in memory.
Can you show the last command?
Right, yeah.
So df.head spits out the top 5 lines by default of the data frame. And look at, you've got a bunch of columns here, 21 columns, and they're all different kinds of columns, right? So we're going to go through the process of figuring out what columns we're going to use, how to turn them into vectors, how to train a model, step by step. Cool. So let's just check, one more thing you can do is check on the full shape of this thing. So df.shape tells us the shape of the matrix that this data frame contains. So what does this mean? 7,043 rows, 21 columns. Okay? So this is just an abstraction, an extension of this. This is a very simple idea. This is the exact same thing, right? So the columns instead of 2, there's 21. And the rows instead of 2, there's whatever, 7,000 something. 7,043. And all the computation that works in 2 dimensions also works in higher dimensions, which is something that we'll get into in a moment. But this is a 21. This is a 21-dimensional space. Each of these rows is a 21-dimensional vector. What does that mean? Don't worry about it. Right now, just think of it as a list of 21 numbers for each row, right? And there's 7,043 of them. They're all different types of information. This is very important to understand. We're going to treat them all differently. So we do df.dtypes to print out the data type of everything inside here. So there's a bunch of stuff in here that is objects. We can't do anything with objects. That's not useful to us. We have to tell pandas which things are categories, which things are strings, which things are floats, which things are integers. And we can figure that out by just looking at it. Right? So let's just look at this for a second. One thing to note is all these columns that we're seeing here, there's a bunch that we're not seeing. They're hidden. 21 total columns in this dot, dot, dot. But we can ask it to show us all of them if we want. But in any case, this is, we're looking at some of these columns. We don't know what this data looks like. You might assume that the only values in each of these columns are no and yes. That would make sense, right? But we can't assume that. We don't know what's in these 7,000 rows. So we have to now figure that out. What's going on in this data set? So this is called...
Sorry, one
Yes.
thing. It's kind of surprised. Why is everything an object?
Good question. Object in pandas' universe just means I don't know what this is. That's it. And we can tell it what it is, and then it'll be fun. We're going to do that in a moment. So this is called exploratory data analysis, EDA, which I often do while listening to EDM. So what we're going to do is, the first thing we're going to do is this column, I know for a fact, we're going to take some shortcuts, because I've already poked around this, I know what it looks like, so you're going to benefit from that. There's nothing I can do with this column. I know for a fact that is the case. So we're just going to get rid of it. This is some internal ID that this telco company has. Sorry, I should have maybe stated what we're looking at. This is, as you can tell from the file name, telco customer churn data. I don't think I ever said this. Every row is a sample of a customer. Clearly, every column is information about the customer. Last column is whether they churn. Very important question for a telco company. And a ton of stuff about this. Right? So this is a real data set that I found on Kaggle. And this is actual stuff, which I thought was important. I was going to make a synthetic data set, but this way you can see what kind of real issues come up. So anyway, there's a bunch of stuff in here that I know is garbage. This is garbage. I'm just going to drop it out. I can't use that. A human cannot process that information. Certainly a model cannot. So I'm just going to drop that column. So I'm going to say I want to assign to my data frame the output of df.drop, and I'm going to pass it the columns that I want it to drop. This is dropped in the column. Okay, so this will get rid of customer ID. So now if I ask it df.shape, what should it say?
20.
Yeah. Okay, the next thing we're going to do is, so I'm going to iterate over the columns in this data frame, and I'm going to ask it to tell me how many unique values does that column have. Because we don't know how many unique values each column has. If it's a float, right, it's going to have 7,000 unique values, because it could be anything. But if it's a categorical variable, it'll have 2, 3, 5, 15, whatever. We don't know yet. We don't know what is in these cells. Just some CSV we found on the internet. So we're going to do 4. So remember, df.columns gives us all the columns, right? This is just basically a list of strings. So we can do something like this. For column in df.columns, now you see why we have to learn Python first. We're iterating over this list, and we're saying, I want you to check the, don't type this out just yet. I'm going to build up this command. I'm going to do this over and over. So maybe follow along and then run it afterward. Check the column in the data frame and get the count, or get all the unique values in it. Okay? Then take the length of that list, the length of the unique values in that column of the data frame, and assign it to a variable called nonlinearities. And then I just want you to print it out. Or maybe I want you to print out the column name, and I want you to print out a little dash, and then I want you to print out how many unique values were in that column. Okay, so what is this now? Online backup, online protection 3. These are columns that we thought had 2 values. That is not true. We don't know what's in there. There's 3 values. It could be a missing value, it could be missing data, it could be anything. It could be a comma, it could be someone typed the wrong button in. This is what happens in real data. So, okay, let's figure out what's going on.
Sorry, Vidit, can you just
show the code?
Sure.
Can you just explain that again?
Yes. For every column in the list of columns in this data frame, and now so to read this, let's go from the inside out, which is usually a good approach. Take that column, so now you've got just a bunch of information from a column. Take the set of all unique values in that information, and then take the length of the set of unique values and store it in a variable. Another way to do this is I could say unique values equals df column dot unique. And then I could say print the length of unique values, or store the length of unique values into non-values. And it's going to be the exact same thing. This is just a little bit easier to follow, probably. Another thing we could do is say if the number of unique values is small, let's say it's less than 5. I see 2 kinds of values here, stuff less than 5 and stuff way bigger than 5, right? So this is going to print out, maybe let's just reverse the order here. So it's going to print out the name of the column, a little dash, the number of unique values, and then if the number of unique values is less than 5, it's going to print out what they are. So we're going to see what these are, right? Female and male makes sense. 0 and 1 for senior citizen. Yes, no for partner. But now we see what's going on down here, right? Yes, no, no internet service, which they put in their matrix, which we have to now deal with. This has 3 values, month to month, 1 year, 2 year, etc. So these are, what kinds of variables are these?
Strings.
They're strings, great. They're categorical, right? This is not a regression task, this is a classification task. Great, so now we know what's in there. What we're going to do is tell pandas to deal with this stuff in different ways. So we're going to say, well, we can actually do it right in this for loop we already have. I'm not going to print anything anymore. What I'm going to do is tell pandas that if there are fewer than 5, I think we saw was the number for categories. If it's fewer than 5, I want you to set that, I want you to remember that that column, this is kind of weird syntax, but it is sort of what it is, that it's a categorical, sorry, not categorical, category. So I'm just telling pandas, if you see less than 5 values, unique values in that column, I want you to treat that column as a category. So I'm just going to run this, it's not going to print anything. So it ran. And now, if I do df.dtypes, dtypes, voila. Right, so no more objects. Everything that's got less than, oh, there's one object. Total charges. I couldn't figure out how to do total charges. So why is that? I know after having looked at this data, there's actually missing values. So this is what happens, right? So the next step after this is to deal with this one column, which we think is probably important in featurizing this matrix. What we're going to do is forcibly convert it to a numeric type. So the way that you do that is I want to set that column equal to, so I'm going to call this function pandas called toNumeric. And I'm going to convert that column. Okay? When I run this, it's going to fail. It's going to fail because it cannot deal with an empty string. Okay? Which is what I told you was the issue. So in some row, there's an empty string. Doesn't know what to do with that. So I don't want to go in there and clean this. I don't want to deal with this. I don't care about one sample or some small number of samples. I'm just going to say, I don't care. Errors equals coerce. So forcibly convert that data to numbers, however you see fit, ignoring missing values without complaining, please. And it does it dutifully.
Can you just explain the last 2 things you did?
Yes. So basically, we had all this information inside this matrix. We have to tell pandas what kind of data it is. because it's going to make it easy for us to build vectors out of all this stuff, right? So anything that was an object before, we couldn't do anything with. So we went through all of the columns to look at what kind of stuff is in there. And if it was only a few different kinds of things, we just treated it as a categorical variable. But if it was a lot of different kinds of things, that's not categories. It could be a number, it could be a floating point number, it could be an integer, it could be anything else. String, right? So if it's like a text field someone typed into, that's just strings. People type in all kinds of stuff, not n different things. So we went through all the columns. We forcibly set multiple types to categories. One column failed, even though it is a category. Or is it a category? No, it's a float. It's total charges. It failed. It failed because we were missing data in the matrix, which I could have taken it out before I uploaded it, but I didn't because it's, it's how you find stuff on the internet. And then we used a function in pandas to forcibly convert that one column. Does that make sense?
No.
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 No. So what is the coerce for?
Okay, well, literally the reason it's there is because when I ran this without the coerce, it failed. And pandas, people who wrote pandas, they know this. They know the data in the real world is messy. And maybe you'll have 5, 6 samples, whatever, that have some missing value, and you don't care. So you just say to it, ignore those rows. Or you say to it, just put 0 in for those values. In this case, it's putting 0 in for those values. Or sorry, it's putting in nothing for those values. And that's going to be an issue in a second, we're going to deal with it. So,
Just for those, though.
just for those, just like 5 cells that are missing. So how do we check what's going on inside this thing? We're going to do df.isNull, which is a method that returns all of the null entries inside this data frame. Get the values of them, and then see if any of them are null. And the answer is true, which means some of them are null. So, I mean, this is just a chain of methods. It might be confusing why I've chained them up this way. You can always decompose it into individual method calls. This is just a data frame that is false everywhere that there is data. So when I do .values, I get this as just a big, where'd it go? A big array, not a data frame. And when I do .any, that's a method that you can run on arrays that tells you if any of them is true. And some of them are true. So some of them are null. Okay? So what do? I don't know which ones are null. They're somewhere in this giant matrix. I don't want to deal with it. So I'm just going to drop them. And they're gone. Okay, so, sorry, this new thing that it spit out is with them gone. I want to assign it to df. So I'm going to put it into that. Great. So now, df doesn't have any NA values at all. And now we can run this guy again. Should be false.
So you remove all the errors.
Remove the errors by removing any rows that have missing data.
So what's put in place of the missing data?
In this case, they're dropped. Just drop the rows.
Just drop the whole
Drop the
row.
whole row.
Okay.
Can you check how many you dropped?
Yes. 43, 33 down to 32. So 11 rows disappeared. This happens all the time. You're just like, I don't want to deal with it because there's messy data all over the place. If you can get a clean subset where every value is filled in, that's ideal. But if you're missing values, what are you going to do? Everything has to go in as numbers, and you have to make up numbers then. You make up numbers based on what the other numbers, what the other values in that column are. That's what people use it. It's called imputation. But you're just making up data, right? There's no information there. Cool. Clean it up. We're done. This is the boring part. Now I think a little bit more fun, feature selection. So let's just check what we have now. We dropped some columns, we did some cleaning. It's not dtype, right? It's types. And everything is now a type. Nothing is an object. Everything is something that it understands. Right? Categories, integers, and floats. Fantastic. Okay, so now we want to actually look at what the inside, what the floats, what do they look like? The categories, what do they look like? What's the distribution across the values in each of these features? So how are we going to do that? We're going to import another library. This is called matplotlib, lots of weird names. I'm going to, again, do it idiomatically. But this, I guess this plus TensorFlow, and we'll be done in terms of importing random libraries. This is how you do it. So matplotlib, why is it so ugly? I don't know. I wish they hadn't made these bad decisions with the names like 15 years ago when they made this and they started this stuff. Because this is very ugly, right? Ideally what you'd want is that the canonical Python library is called like plotter or something, right? But that's not what it is. It's matplotlib.pyplot. Because it wasn't made by the Python people, it was made by other people. They named it whatever they want. But now everyone uses it, so we're stuck. So we imported this PLP, everyone does this. This is a similar pattern from before. So for every column that I have, please plot a histogram of that column. And I want you to just title the histogram with the column name so I can keep track of what's going on, and just show the plot. Making sense? Shift enter. Lots of stuff happens. Still churning away. Tons of plots. Okay, what are we looking at? We're looking at feature distributions for the features of our data set. The first feature is gender. It's a categorical variable. It looks like the data set is split evenly on gender. So this is a bar chart, the histogram. 3,500 samples with female, 3,500 with male. Senior citizen, mostly zeros, mostly not senior citizen. Have a partner, kind of, basically split. Have dependents, more people that don't have dependents. Tenure, how long they've been using the service. I don't know what the units are here, I think weeks probably, but we'd have to go ask whoever made this data set to find out, because it wasn't in the header name. Whether they have phone service, etc., etc. So these are just all our features, all the values. Let's see if we can find a float feature. Here we go. So this is monthly charges. This is what the distribution looks like. A lot of people not paying much money, a bunch of people paying a lot of money. So what do I see when I look at this? One thing I'm thinking is, well, it seems like it's important to know whether they're here or here, right? That seems like an important thing, just based on the nature of this distribution. If I'm just estimating sort of what the data generating process is for this feature. So what I might choose to do is create a new feature called monthly charges greater than 30. And then I'm explicitly encoding for my model that information in a new column where I compute the value of that column based on what I already have. I'm not going to do that now, we're just going to treat it as a number, but that is an option. It's called feature engineering. So you're just looking at the features, looking at the information contained within them. You as a human know how to suck that information out. You can help the model by putting information into the matrix from the real world before you even train the model. And that's called feature engineering. And so one kind of thing like that would be for me to split this distribution into two and say, if it's less than 30, I want to have the value of the column be 0, and if it's bigger than 30, I want it to be 1. That's just my guess for what might be useful. We don't know. We can train both models and see how they perform. Total charges, also an interesting distribution. Very few people pay a lot of money. And then churn, most people stick around. Great. So we're trying to basically predict this class, right? So the next thing we need to do, after we know about all our feature distributions, nothing looks too wonky. I'm satisfied with what's in this data set. Everything is clean. Now let's start building our training and test data sets, which was that next step. So next, build data sets. So the thing we want to predict, the label in this data set, is what column?
Sure.
So we're going to take it out of the matrix. We don't want to feed in our labels into the model because we don't want it to see the labels when it's trying to guess what the answer is. Will make sense in a second. We're going to take labels out by using pop. So pop just says take this out and put it into the variable. It is no longer then in data frame. We can check that. So now labels is 7032 by nothing, so it's a vector. This comma here just tells you there's no second dimension. 7032 numbers. that are just 1 or 0, right? You can put it out. Well, yes or no. And what else can we do? We can. Yes, okay. Right, so what we're going to do is we're going to drop out some of our, we're going to try to keep only the categorical variables. There's a reason for this. We'll get into it in a second. So I'm going to create a new array, categorical columns. I'm going to say for column in df.columns, if the data type name, dtype.name, is category, I want you to append the category name to my list. Well, oops, the battery's low. Sorry? The question was, can I explain that? So basically, I wanted to know which of my columns are categorical types. And so in this array now, I iterated over all the columns, that's what they were. If they were category, I appended them to this list. So I can print out categorical columns. It's going to be a list of the names of the categories that were categorical. Okay? And then the last thing I'm going to do is, so this is an important step. It'll be clear why I picked out the categorical columns first. Remember that I said everything has to be a vector when it goes in. These are columns with, they're all categorical columns. They can all have multiple different potential values. Some of them have 2 values, some of them have 3 values. We saw, I think one even had 4, right? So how do we deal with that? There's a few options. One is, we could, if there's 2 values to that potential column, we could say one is 0 and the other one is 1. And then just plug in 0 every time it's the first value and 1 every time it's the other value. A much cleaner way to do it is what's called one-hot encoding. What does that mean? So maybe that's the board. I'll try it on the board. So basically, gender can have the values male or female. So instead of having it be one feature with the value 0101 for male or female, what we're going to do is turn it into 2 features. Gender female and gender male. And gender female is always going to be not the same, right? So gender female is going to be 1 when gender male is 0, and inversely. We're doing this because we want to make it easy for the model to understand this information. Yes?
In that case, when it's binary, do you need both columns, or can you just have one?
You don't, if it's, because that's redundant information. If there's 3, then it matters.
Yep. Then you would need 2 columns.
Yeah. But we're going to use a method built into pandas that handles some of this for us, and it's just going to expand into the number of columns that equals the sort of number of unique values in that column. If that makes sense. So how to do that? We're going to use a method called getDummies. And whatever this returns, we're going to assign to a new variable called features. So we made a labels up here, which was just that one column. We went through the categorical columns in the data frame, all the columns in the data frame to get the list of categorical columns. We took that list and we fed it in to this method, which will, for each of those columns, explode it out into multiple columns in the way that I just described. So we're just going to run this. Oops, not dums. That's what you write if you're dums. Dummies. So features.shape is going to be way bigger. 46 across now, because it just blew up all those categorical columns. Make sense? Cool. And we can see what the top of it looks like. 5 rows by 46 columns. So you can see gender female, gender male. Senior citizen 0, senior citizen 1, etc. So this is one way of vectorizing information. And then labels is obviously the shape that it was before. Cool. Now, so the next step is we had yes.
One question. So what is like labels, features? Are those like names of some data sets that you're creating from the data frames?
So features is a variable. I could have named it whatever I wanted. I created the variable by selecting, by asking pandas to build a new data frame out of my old data frame by blowing up categorical columns. And whatever comes out is a data frame, it's another data frame, and I store it in features. So features is another data frame.
So you have the data frame, which is like the original one, and then you have features, which is that one, just with more columns, like you said.
Yeah. So df still exists in memory. I didn't overwrite it. I could have, but I want to keep it around. Cool. Okay, this is an important step. So this is splitting our data into training and test sets. We don't have to do anything with this. Fortunately, scikit-learn has a function built in that just does it for us, which is kind of a theme. So how does it work? The function is sklearn.model_selection.train_test_split. So if you didn't know how to use this, you can just hit question mark, shift enter. Oop. Oh, I know what you should.
Excuse me?
Yep.
Could you explain what is PD standing for?
Oh, PD is pandas. So at the beginning, I don't know where we did this, a while ago at this point. We imported some libraries, NumPy we imported as NP and pandas as PD, and I explained that it could have been whatever we wanted, but this is what everyone does.
And what is pandas doing again?
Pandas has, the main thing we use in pandas is data frames, which, so we use pandas to very easily pull a CSV into this object that we could just work with and get columns and all this stuff. Because a CSV is just a bunch of text in a file, right? So pandas has functions in it that will go through all the columns, read them, give them methods, and let you do stuff with them, like dot columns, stuff like that. And then a ton of other utility functions. You could have also done this without pandas. You could have said, you could have iterated through every row of your text file and then just built values. That was an option. But I wanted to give you guys exposure to pandas, because it's pretty popular and common. So, and it's less typing. So, cool. So, exploring features, built our data sets. Okay, so why isn't this working? The reason it's not working is because this might have been hard to figure out if you didn't know what to do. This is the right way to import that method. The reason is just because whoever wrote this, they didn't do a good job. They should have made it importable like this. All right, not like this. I should have been able to import sklearn and then just call it like this, do whatever I wanted, but I cannot because of how this was written. So that didn't work. So I can do from sklearn.model_selection, just import this one function. Okay, and that'll run. And then I'm going to make my training data. So the way I do that is by splitting the features and labels that I've accumulated into two chunks. And it's important for me to maintain knowledge of the indices in the features object and the labels object, because the correct answer for this row is this row in the labels object, right? So you can't mix them up. And train test split will do that for us. So the API is train test split features. I think it's features and labels. Yeah, features and labels, and what it spits out is 4 objects. It spits out xtrain, xtest, ytrain, and ytest. So I'm going to run this and I'm going to explain it. What is this? So if you recall, so what was features shape? 7032 by 46. Labels shape 7032. Great. Xtrain and xtest are going to be subsets of the features matrix. Yes?
How are we splitting it? Is train test split randomizing the data and splitting it that way?
It should. Yep. So this is what I would do if I had that question. This is like, there's no way to tell. The point is you can't tell from within Colab, right? That's a great question, right? So you have to go check the API documentation, or you can always just, so basically everything we're using, the way that it works is completely accessible to you. All this code is open source. You can always just go see what the code is actually doing. And it's all on GitHub. So I can just do this, and I'll probably find the function somewhere. It'll be a nightmare to read, but it'll explain what's going on for sure. So this is where it is. There's probably some def train. There it is. Right, so this is the function that we're calling. It's in the virtual machine somewhere in this Google Data Center computer, and this is the code somewhere that does train test split. So you can always it's telling you about the method you can pass. I can pass shuffle equals false, and then it won't randomize. So this is just, you can always go do this. You can go look at the source code, and you can go look at the API docs as well. Cool. So we were saying features shape is 7032 rows long. Xtrain and Xtest are going to be a subset of features. So I was saying before, if, that data set we had on screen, we're going to split it. That's what this is doing. It's just kind of cutting it at some point. So it decides that split on its own internally. It's usually 80-20 is a very common split. 80% of the rows staying in the training set, 20% in your test set. But you can change that. It's not set in stone. So what is Xtrain's shape? Smaller, right? It's because it puts some of those rows in Xtest. Cool. And then Y-train, it should be the same height as this, same number of rows. If it isn't, we've got a problem. Right? So 5,274 ones and zeros, 5,274 rows with 46 columns in my training set. Cool. All our data is built. Now it's time to actually train a model. Model selection and training. Actually, I'm going to make this text here.
I think we have a few questions.
Yes. Sure.
Sure, I got the difference between Xtrain and Xtest.
Great. Okay, so let me do some work. So what happens when we fit a model? What happens is, so say we have, again, we're going to have two features. Say they're both numbers. This is a float, and this is just an integer. And then what I was saying is the point is to learn the values of some parameter vector so that you can consistently get the right answer at the end. Right? So this is, and then when I broke this out into equations, what it was theta is a vector with two numbers in it, a and b. Use Greek letters to impress your friends. Alpha and beta. And x is a vector, it's one row. Yeah. Whatever the values are. So 0 and 3.2, 1 and 2.1, right? But you only have one alpha and one beta. You have a ton of samples, you have one alpha and one beta. So you want to multiply that alpha and that beta by each of these things such that for as many answers as possible, you get the right answer. Okay? So how does this work? How do you get alpha and beta to be correct? The way it is universally implemented in most machine learning algorithms, unless the math is very convenient, what you have to do is pick random numbers for alpha and beta. That's how you start. Pick random numbers, let's say 0.1 and negative 0.2. Doesn't matter. Then we compute this for every row, and some answers come out. And they're all completely wrong. Right? They're completely random. Alpha and beta are totally random. So what we do is we check what came out, what we predicted. So we did alpha, beta times this. So this is a dot product. If you haven't heard that before, all that means is multiply a vector by a vector. You don't know what that means. All that is literally multiply these two together and add that to multiplying these two together. That's what vector multiplication is. This is just going to be this And it's going to be some number. This is some number, 0.1, this is some number, this is some number, this is some number. 4 numbers. And some number comes up. And it's wrong. Right? So the correct answer we had over here. And so now, I forget who asked a question about why we're doing a training test split. The reason we do a training test split is because, let's say we split it here. This is, and you say this is a training set, and this is a test set. The model is only allowed to use these samples to learn alpha and beta. And then, in order to see how well it performs, we show it this sample, we see what it predicts, and we see how wrong that new sample is. This is very, very important to do. You cannot just treat all the training data and feed it in and learn theta. Because you can, first of all, that's allowed. You can do this, right? But what happens in practice, people have learned, is that when you run the algorithms that learn the best value of theta, which is something that I'm not going to get into because that's a little bit too much now. But if you learn theta, you often will have, what am I trying to say? You initialize these parameters randomly, but when you're fitting them, you're trying to minimize the error across all of your samples. And you only have one alpha and one beta, so you only can choose these two numbers. And then what people have found empirically is that if you do not split into two sets, alpha and beta will be numbers that are perfect for your data set and are completely bad as soon as you get a new data. These numbers will overfit, it's called. So to prevent the numbers from being too perfect for our data, we try to test how good the model is with data it's never seen before. So that's the idea behind the training test. Is this making sense? Kind of. We're already at 12:10. So what I think I'm going to do, we're just going to train this model, and I think we should probably take a break after that. So this is very simple. The beauty of scikit-learn. I want to make a model by calling the logistic regression function inside the linear model module of scikit-learn. And it's a function, or it's a class technically, but I'm going to use open close paren. And then what comes out is a logistic regression model that has not been fit to any data yet. Same issue before. Okay, so from sklearn linear model input logistic regression, no open close paren, and then I'm going to do model equals. I'm going to call that object and put it in the model. Great. And then, so some amazing magic is about to happen. When I call this function, it's going to learn the best values of theta with the data that we're feeding it, with xtrain and ytrain. And we're not even showing it x test and y test, which we've set aside. So it'll be clear in a moment what we're going to do with that. So let's run this, and it's done. So 5,000 rows, it fit parameters for effectively performing logistic regression, which is a machine learning model. So it trained it already. That was model training is complete. So now we want to see, why was it so fast? Because computers are very fast, it's very small data. How well did it do? So we're going to ask the model to score itself using the test data. So we trained it on training data, and we're testing it on testing data. What is the score? It is 0.79. What does that mean? So to understand this, we will get into the idea of what's called a confusion matrix, which might be inducing some confusion. What we're going to do is ask, so what we haven't done yet is gotten a list of predictions with our test data. So we're going to get that. We're going to do, please predict the correct values of y. So run inference using the parameters that you've learned, the parameters for logistic regression, on a sample. So you're going to do, well, on a bunch of samples, on all our samples. So ypred is the model's predictions for this test data set. Yes?
So the reason why our score is different from yours is because the training and test set is standardized for different people.
Correct. It's not going to be exactly the same number. So there's ways to make it so that you're getting exactly the same number. Internally, Python and NumPy use a random seed, which you can fix at the start of your notebook or the start of your file and say, hey, NumPy, use this seed, and then it'll be fully deterministic. But it doesn't matter. Yes?
In the background, is this essentially just doing a bunch of simulations to get this number?
This is performing gradient descent on a parameter space. So what does that mean? It is taking a bunch of samples. The samples are our data. So it goes through 5,000 rows, and it initializes random parameters. It computes the output of the logistic regression function, which is very similar to this function. There's only one change to make to this function to get logistic regression, which I'll show you. And then it changes the values of alpha and beta bit by bit to make the answers less and less wrong. That process, changing the parameter values bit by bit to make the answers less and less wrong, is called fitting the model, or often it's implemented as gradient descent. So this is something we can get into if you'd like, but it's a little more involved, and I left it out on purpose because the way that models are fit, I don't think it can be done without a lot of whiteboard. So happy to get into it if you'd like.
So the score is just the R sample R squared.
It is not the R squared. So what is the score? I'm going to explain what the score is. To understand what the score is, we need to produce a confusion matrix. A confusion matrix captures the entirety of how well your model performs, more or less. What does that mean? So I'm going to call the confusion matrix method in scikit-learn. And I'm passing in the correct answers and the predicted answers by the model. Okay? And I run this, you get this little thing out. So what is this? What this is saying is, so each row tells you about what the correct value of the label was, and each column tells you about the predicted value of the labels. What does that mean? When the actual value for churn was 0, the model predicted 0 1,151 times. But when the actual value was 0, it predicted 1 135 times, which we don't. We want it to predict, I'll do this on the board. This might be confusing. So the conventional way to write this is, so what are our class label values? There's only two values, right? So the potential true values are 0 and 1. And the predicted values, potential values that the model could possibly predict, are also 0 and 1. So, and we know what all the right answers were, and we know what all the wrong answers were, and we have 5,000 whatever samples. So what we can see is of those 5,000 samples, how many were 0 that the model actually said 0? How many were 0 where it thought it was 1? How many were 1 where it said 0? How many were 1 where it thought it was 1? What we want is for this number to be big and this number to be big. And these two to be very small. These are wrong. Right? So in what's happening here is 1151. So there are 1151 samples where the true value was 0 and it predicted 0. Great. But it got it wrong 135 times. And then it was 252 times when it got it right, when it was actually a churned customer, but it also got it wrong 220 times. So how do we interpret this? Well, first of all, the more stuff is along this diagonal, the better. Like I said, so you want the off-diagonal components to be 0. That's not true here, right? But these are different kinds of mistakes. So this is a mistake where the person did not churn, but the model thought that they churned. They would churn. So what does that turn out being in practice? If you're implementing this model, some rep goes out and reaches out to this customer, they were never going to churn, it's a waste of time. Right? So you don't want a big number here because people are going to act on the results of your model. You're just trying to predict who's going to churn, and you want very few in this case, false negatives. Because the true label here is negative. It's not going to turn. And this is a false negative because your model said that they were going to turn. You were wrong. It's false. And this number here is false positives. Backward. Yeah, exactly. This is false positive, false negative. So positive because the model said that it was 1, but it was actually 0. And then false negative because the model said it was 0, but it was actually wrong. So you were wrong when you said it was a negative sample. So this is maybe a bigger issue, right? If you're a telco, you care more about making sure you don't want to waste rep time. You don't want the model to predict that someone's going to turn when they're not going to turn, because then someone makes a call and they waste time. But you certainly don't want the model to say this person's going to stick around when they're not going to stick around. Right? You want to reach out to every customer for whom the true label was 1. Does that make sense? Cool. Different kinds of errors. So now to close the loop on what the score is. So score is, in this case, it's accuracy, which is true positives plus false positives over everything. And there's other things you can compute. There's many ways to combine these 4 numbers. There's a Wikipedia page on how to do this. There's a bunch of other terms like recall, F1 score, all these things. Ultimately, what they do is they weigh to different degrees different kinds of errors, right? So you can imagine a kind of problem where false positives, where the model thinks that, so in this case, a false positive is kind of bad because it's a lot of time wasted. Imagine a model that predicts whether someone's going to get cancer. Right? So there, you are absolutely fine with false positives. I'm fine with telling people that they might have cancer if they don't, because then I'm going to go investigate, I'm going to do a biopsy, and hopefully they're fine. I'm not fine with telling people they do not have cancer, they can go home, and they have cancer. Right? So in that case, you want false negatives to be very small. So this is just thinking about sort of the implementation of a model and what matters from a product perspective. Cool. So that's model metrics, so logistic regression. I think that's a natural place to probably break. I planned to do this till 12. We're past that. But I think we could do, so maybe break for lunch, and then I'll try to rework some of the other material to do it quickly. We could do it in like 20 minutes, half an hour afterward, if that's something people want. Otherwise, what we can do, this is enough, right? So you have the basics of scikit-learn. You could just sort of download additional data and start trying to work on this stuff. I'm fine either way. But definitely probably break for lunch now.
Yeah. So let's break for lunch. We have lunch there. And if you haven't checked in with Obagu right there, please make sure you check in. And that's it. If you are still playing catch up, this is the time you can like do all the stuff that you're doing.
I'll play you. What do you like?
There we go. Cool. So, for vector machine, k nearest neighbors, and logistic regression. What's going on here? Decision tree. So, what decision trees are trying to do is find specifically axis parallel decision boundaries. So you can imagine the logic here is, let's say we had some linearly separable data set. The way a decision tree would think about it is, it would just kind of walk along this axis and see what value of this is a good place to slice this up. And then once it's done that and realizes this is a good place to slice it up, it'll do that for each of these independently. So it's going to say, okay, well, anything below this I have no certainty. Above this I have no certainty. But I know that in this box, it's O's, and in this box, it's X's. So like literally there's a function that's going to see for what value of x1 and for what value of x2, you can find these axis parallels. But as you can imagine, that does not always carve up your space the way that you want. This is kind of awkward, right? Another thing you do is just mix a bunch of decision trees together, which is called a random forest. So what you do is you train a bunch of decision trees, 100 of them, and they all learn slightly different boundaries, like one's over here, one's over here, one's over here. And then you train a second model that figures out how much to weight the predictions of each decision tree. But you can see the output is kind of visually similar because it's still all these axis parallel decision boundaries and not anything like this. And then, what is this? This is a neural network. So certainly has stronger confidence about the location of the boundary compared to logistic regression, which had no idea what was going on, right? It's barely sure where reds and blues are, whereas this guy's pretty sure. He says, I'm pretty sure all this is very red, all this is very blue. I'm not so sure about this region. It's a richer model family. You can capture more variability in the data. Okay, so that's moons. We can kind of do the same exercise for circles. Logistic regression fails. Very interesting. But you can, so this is a perfect example of, so say this is your space. Say your model is like a fraud predictor or anything. It's some model that makes actual decisions in the real world for real people. This is the decision space that I've learned. There's people who are going to get misclassified out here. Well, maybe this is not the best example. There's definitely people who are going to get misclassified in some of these. So this is, gross misclassification of some people sometimes. And so this kind of gives you a sense of, again, random forest axis parallel boundaries, but better at finding this class than the other class, it looks like. Oh, I've been ignoring the accuracies. So we have accuracies for all these two. We can see that they'll go up, and the confusion matrix will improve as the model complexity goes up. So, well, they should go up. They don't universally go up, but I've ordered these by increasing the model complexity. In general, they'll go up. There's also a bunch of other stuff here. What is all this? So for each of these models, there's a bunch of levers you can pull. They're called hyperparameters. We didn't even talk about them. But the idea is you want them to be the best values to produce the best validation accuracy on your data. Often what people will do is just try a bunch of values and see what comes out and then change them intelligently. It's called hyperparameter optimization. Hyperparameter optimization. Cool. So last, make circles. NLP learns circles pretty well, like very effectively. And this is a linearly separable data set. This is the last one. Very easy. So they should all do pretty well on this. Logistic regression figures it out. K-nearest neighbors figures it out. Or vector machine figures it out. Easy, right? Decision trees thinks this is a joke. So I hope this kind of gives you an intuition for how models work in two-dimensional space. Not all these intuitions make sense in high-dimensional space. The reason that they often fall apart is because volume does not work the way that we think it does in high-dimensional space. So what I mean is, if I'm standing at this point right now, there are, what it means to be in 3 dimensions is there's 3 orthogonal directions I can move. I can go this way, I can go this way, or I can go up and down. Right? So the number of directions you can go in scales with the number of dimensions. So linear, right? So if you're in 40 dimensions, at every point, there's 40 directions you can go, which is something we cannot conceptualize. But that is why volume doesn't work the same way in high-dimensional space. Volume goes up the cube of the number of dimensions. This room has, let's say the side length is d, the volume is d cubed. So for an n-dimensional space, it's d to the n, which is huge. There's a lot of emptiness in high-dimensional space, which is hard to think about until you start messing around with it a little bit more. But at the end of the day, these principles still apply in terms of precision boundaries, optimization, et cetera, et cetera. So this is most of what I had planned today. I had a section I was thinking about doing on TensorFlow, but I feel like it's going to be a lot of new stuff that's kind of, it's going to be too much. So I'm going to skip that. I'm happy to talk about TensorFlow with people afterward if they're interested. So what I was hoping to do from now on is...
Can you give a high-level overview of TensorFlow?
Sure. Sure. So maybe we'll do it without code. Just so that, I guess maybe what's useful to understand is deep learning. Cool, let's just do that. So we'll do this for like 10, 15 minutes. Feel free to ask questions about deep learning. Then the idea is if you downloaded that zip file, there were a bunch of other data sets in there. So I tried to find interesting ones. There's one with a bunch of reviews of wine. So you can train a model to figure out if it's possible to predict the numerical rating of wine from the text of the review. Or many other things, a bunch of columns from Wine Spectator. There's a scraped data set from the Google Play Store. So it's like all this information about apps, and you can try to predict the rating as a function of what category it's in, or how many downloads it has, whatever. So yeah, there's a few things in there. The idea is, after this, we'll split into groups, and just tinker around with this data, use your Colab notebook, use all the stuff that you've put together so far, and see what you can come up with, just to kind of get your hands dirty and do some actual stuff. Okay, what I was going to do was talk about deep learning and how it connects to all the rest of this stuff. And the reason I think it makes sense to do it on a board, can we bring this up a little bit, maybe? I'll just do it on the whiteboard. Oh.
Let's those boards as well.
Oh, great. Sure. Cool. Okay, let's go back to linear regression for a second. We're going to go back to the toy model. So two features. One's categorical, let's say it has values 1 and 0, one's a float, 3.2 and 2.7, whatever. And we have some values, some class one predict. Okay. So what I said was with linear regression, what you're doing is fitting some parameter vector theta.
Can everyone see that?
I don't know.
Is there a way to turn off the cross degree?
Yeah. So let me just keep this. Nope. Downstream. Cool. So what I was saying is that the point here is to learn two numbers that make this true as often as possible, where the thing you predict is as close as possible to the actual value. Right? That's linear regression. Logistic regression, which we didn't talk about on the board, but which we implemented as a function, does one more thing on top of this, which is adding a nonlinearity. What does that mean? So this operation is fully linear. I'm going to just do a one matrix multiplication on the board so that everyone knows what's going on. So for any matrix, matrix multiplication is like universal in machine learning, and it's the easiest thing. So if you just put it in your head once, it's useful. So if I have some m by n matrix, it's just m times n numbers in a grid, right? I can multiply it by any object that has the same dimension. I cannot do this if it's p times n. It's not defined as matrix multiplication. Right? And what you get out is n times p in shape. So what does that mean? Let's do it with an example. Let's pick m by n to be 2 by 3. Always rows first. 2 by 3 matrix. Let's pick x to be, we're going to use, let's say, x1, x2. So this is a 2 by 3 matrix, and this is a 2 by 1 matrix. Can I perform this matrix multiplication?
But on maybe use a different plan. It's a little hard to.
It's hard to see. I'm also writing sloppy. Can I perform this matrix multiplication? I heard some murmurs. No. Correct. This needs to be equal to this. That's all. So what we can do is just flip it on its side. We can make it 1 by 2 by taking what's called the transpose. Literally all that means is we're going to write it like this. Suddenly this is 1 by 2. Oh, sorry, that's not what we want. We want to write this as 3 by 2. That's what we want. We want to write theta transpose. This becomes, so I turn every row into a column. This is 3 by 2. This is still 2 by 1. And now this is well defined. So what do? This is the actual multiplication happening. The output we know is 3 by 1. So let's just make a spot for each of these. It's going to be 3 by 1, only one thing across. And it's going to be the dot product of this with this, which is, what am I doing? Sorry, this with this. Right here. That's not legible at all. Great. Okay. I hope this is not too much detail, but we need this for logistic regression. We're going to do the dot product of this with this, which is ax1 plus d x2. The dot product of this with this, which is b x1 plus e x2. And dot product of this with this, which is c x1 plus f x2. And a is a number, x1 is a number. Each of these things is just a number. So this is 3 numbers, which is a vector. That's 3 by 1. Yeah? Cool. So that's linear regression. It's just doing this one matrix multiplication. If we want to turn it into logistic regression, we just take that output and we pass it through what's called a nonlinearity. What does that mean? A nonlinearity is any function that does anything other than adding and multiplying things together. So sine, cosine, tangent, x squared, all nonlinear. But certain ones are useful, we've learned. So the one that we use all the time, they all look like this in general. So they're all really small. The functions are all really small for a while and they suddenly become something else. So the point of all these functions is that they're one thing for a while and then suddenly they become something else. This is exactly how neurons fire in the brain. Tons of inputs are coming in, but there's a nonlinearity such that only when the magnitude of the inputs crosses some threshold do they fire. And that's the intuition behind a nonlinearity. That's why deep learning works. It's only because of this function that will do something to the output of theta x. So what does it do? They all look like this. The one that I do here in particular is called a sigmoid function. It'll look a little scary because it has an e in it. But when you plot it, this is what it looks like. So that's not confusing, right? It's just whatever number you put in. Put in 7, the output is 1. You put in -7, the output is 0. If you put in numbers near 0, it could be not 0 or 1. Does that make sense? So all you do is you do sigma of theta x, and suddenly you have a logistic regression problem. So linear regression is just multiply these two matrices together and learn A, B, C, D, E, F such that this works. Logistic regression is pass it through a nonlinearity. So then you get some number that is going to be, the output is this range, right? So the output's going to be at least 0 and at most 1. So just so you know, this is 0 and this is 1. In this graph, if you actually graph it. And that's the difference. And then, so the next step is, we've learned, okay, nonlinearities are important. Did you have a question? No. Okay. Nonlinearities are important because they let us find some magic number where suddenly everything changes. That's the idea behind a nonlinearity. Deep learning is just this concatenated with this over and over. What do I mean? We're going to go through a single feed-forward pass of a deep neural network. I think we'll explain the whole picture, a whole enchilada. So let's say we have some input vector x. It's too small. X. What's our convention right now? They're column vectors. Great. So you have, let's say you have 6 of these. It's 6 features. Okay? And say you want to train a neural network with 1 hidden layer. And let's also say that you have 2 classes. Okay? So what that means is y can take on the values of either 0 or 1. It's 2 classes. And 1 hidden layer. What does that mean? You'll see all these neural network diagrams. They all look like they have, a bunch of circles with lines in them and stuff. What's going on? So I'm representing a neural network with a 6-dimensional input with 1 hidden layer of 4 dimensions and 2 outputs. And what people usually do is they'll draw a line between every single one of these and every single one of these. And the lines are confusing to me. What you've got to realize is that this object, this is a matrix. What's happening in here is a matrix multiplication between the layers. What do I mean? So there's some matrix here that is of dimension 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4. And all I'm going to do is take my matrix, whatever. You could make it 4 by 6 if you want to do multiplication the other way. It doesn't actually matter. This is 6 by 4. This is 6 by 1. We can do x transpose of w. So this is 1 by 6. And this is 6 by 4. And you get 1 by 4 out. Does that make sense? Does that make sense from the matrix multiplication stuff over there at all?
Yeah.
Tracking? Then you pass, this is a vector, you pass it through a nonlinearity. And that gives you another vector, 4 elements, most of which are either 0 or 1. So you're going to literally just take these 4 numbers, I don't know, 7, minus 7, 3, and 0. Then I compute 1 over 1 plus e to the minus 7, 1 over 1 plus e to the minus 7, 1 plus whatever, all these. And you end up with 4 more numbers. This is going to be big. This is going to be small. This is going to be big. And this is going to be maybe a half. Because that's how this function looks. Right? So when it's big, it spits out 1. When the thing that's going in is small, it spits out 0. And when the thing that's going in is 0, it spits out about half. So that's what comes out of matrix multiply times input vector followed by a nonlinearity. And this vector is what goes into this. And then this is another matrix. And we do another nonlinearity. So just doing chained linear transformations and nonlinearities, literally in this high-dimensional space, multiply the vector, bring it to a new point, find a hyperplane, do it over and over, is deep learning. And finding the magic values of all of these w's that does this is the problem, which is what model.fit does. Yes, I saw a question. Yes?
How do you determine how many hidden layers there are and how many nodes are in each input?
Both open questions. So one thing that we didn't talk about at all through all of this is model selection properly, and like overfitting, underfitting, bias, variance. So I'll just do a quick maybe primer on that. We had some matrix, right? Oh, it's always a matrix going in. Let's say it's m by n. M samples, n features, right? There's a bunch of shapes this could take, right? It could be a really fat matrix. We have very few samples and tons of features that you've computed. Yeah? This situation is ideal for a linear model because you ideally have created features that have information in them. And you think a simple model can figure it out. If instead you have some tall matrix, you have a lot of samples, but you don't know much about each of them. And you could go and try to build a bunch of features based on the data that's in here and append it to this and make a wider matrix. But this is exactly the situation that's perfect for deep learning. So simple models for wide matrices, complex models for tall matrices. So simple model, complex model, and then the terms associated with this are this is a high bias, low variance world, and this is a low bias, high variance. What does this mean? High bias means that your model has a strong opinion about the world, or you're feeding it data that has a strong bias about the world. You believe these columns are important. You have some strong hypothesis that you're feeding in your matrix. It's low variance because if you change some of those values, the output of the model is not going to change very much. There's very little variance in the output when you perturb the input. This is just true for linear models. At the other end of the spectrum, you have neural networks, which are low bias, high variance. You've made no assumptions about the nature of the world. It's the raw data. Very few features. It can learn any kind of data generating distribution, whereas this can only learn very simple ones because it has a very strong opinion about them. And it's high variance because if you tweak any of the inputs a little bit, the output will change a lot with neural networks, and that's bad. We try to curtail that. So to answer your question, how do you choose the number of layers and the number of nodes? You're ultimately trying to trade off bias and variance to maximize your model performance. So what you want is, you might think, okay, let's just over-parameterize the crap out of this. Let's just give it, we're feeding it 6-dimensional inputs. Let's make the first hidden layer 500 dimensions. We can do that. What's going to happen is that this model will exactly fit your data and be useless for everything else. It is over-parameterized. And then the inverse is, say you have some really complex data and you feed it to a very simple model, it's going to be under-parameterized because you have a high bias, low variance model instead. So that's kind of a not very useful long answer to your question. It depends on, ultimately you're trying to maximize some metric, usually validation accuracy. So those are hyperparameters. You try a bunch of values and you see how they perform. Any more questions? Kind of a high-speed deep learning tutorial. Great. Oh, yes?
How do you choose your activation functions? Is it just based on the issue?
How do you choose activation functions? So there's a lot of research on this. The common ones are tanh, hyperbolic tangent, rectified linear units, and sigmoids, and a few others. What are these? How do they look? They all look the same, right? So they all kind of do the same thing. Tanh looks like this, I think. It's flat. I should make it exactly. It crosses the origin, that's the point. Right, so this is tanh. This is sigmoid, and I'm just literally plotting, if you plot tanh of x in any plot of Google, whatever, right? This is what comes out. They all look like this. And no one really understands why like one is better than the other. The one that often works the best in practice is a rectified linear unit, and the graph for it is like this. Flat here, 0, and then above it, it's x. So whatever the value is coming in, you just spit that right back out. If it's less than 0, you spit out 0. This works very well. Why? No one knows. There's a lot of theory behind this. In practice, this is not the dominating factor in the performance of your model. There's many, many other things that are going to be a bigger issue. More questions? I mean, I'm here for questions, so yes?
So I think following up on the earlier question, Tim's question, how do you define the architecture of the model, meaning the number of layers you apply, the number of nodes per layer, how do you go about optimizing?
So basically what everyone's been doing is copying other people. Someone does something that works and everyone else copies it and they make small changes to what other people are doing. The whole world of deep learning is pretty lacking in theory. And there's just a lot of empirical guidance on what to do, rather than any sort of analytical explanations for why you choose this over this, or why you do this over that. But I guess the long story short is, you try a bunch of stuff and you see what maximizes validation accuracy. And then intuitively, like sort of heuristically what you want to do, if you have n input dimensions, a typical vanilla feed-forward multilayer perceptron will have fewer and fewer. So you'll have some tall input layer, fewer, and then 2 classes. This is a very typical way of doing it. And the idea is that, these suck out more and more information from your input vector and a more and more condensed representation until this vector contains all the information you need to make this decision. That's what the model is trying to do. So that's why the layer sizes shrink. But there's other ways to do it. Cool. So with that, I guess, so those of you who downloaded the data.zip file have multiple additional data sets. I stopped sharing the screen here, but yeah, so the other data sets that we have are, there's a few that I think are cool. Is this coming up? Great. So, what do I have? Okay, so there's 5 in here. Avocado prices in different markets over time across the United States. A ton of features for apps on the Google Play Store, scraped off of the Google Play Store. Data on every Olympic athlete ever. This is a pretty big table. I think 10 or 15,000 text reviews of wine. We didn't deal too much with text data, but if anyone really wants to work with text data, I can show you guys how to do that, like one-on-one. And then the one that we just used in case you want to want that some more. So there's 4 additional data sets here. So the idea is everything, I've structured everything in this notebook so that you can literally just change the name, if you follow along, you can just change file name here. Where is it? Here, right? And then all codes is going to work, not exactly as is, there's going to be issues, but you can follow the procedure through this with a different CSV and kind of, build your model, split your data, do it all on your own, figure out what you're going to featurize and how. But yeah, that's it. That's it for me. Thank you guys for coming. I'll be sticking around for the next couple of hours to help with this stuff for as long as people are around. I hope you guys learned some useful stuff, and I hope this makes it harder for people to trick you by saying words about deep learning and machine learning. Cool, thank you.
Guys, we're going to publish a link to a quick survey. It'll take you less than 30 seconds. If you can fill it out, it will really help us understand what we did well and what we can improve on. So,
One question for everyone. What would you recommend as the next step for learning?
That's a good question. I actually have, I guess it depends on what you want to learn. What is it that you want to learn? What's useful in this audience? Because I can point out some books, but they might be not the right thing.
Whatever you think. I know there's scenarios.
Sure. So there's a few really good, if you want to get into the weeds, I can point out a bunch of books for that. These are kind of the standard books for machine learning. If you want to get into the weeds. And if you don't want to get into the weeds, what you could do is just Google for, so honestly, your best friend is GitHub. Everyone should know about GitHub. This is where the whole world shares their code. So you can just go here, and if you're interested in deep learning, text, TensorFlow, you just do this, and you will find a bunch of repositories in Python, a Jupyter Notebook itself, which is exactly what we're doing today, that will all help you figure out how to do this stuff. So this is a great approach. Just look at other people's code and figure out how to do stuff. Yes?
Maybe to flip this question, as business leaders, like non-technical people, how much do you think we should learn about this?
So I think you should absolutely understand. Well, let me try to illustrate why I think this is important. Increasingly, it is going to be true that the shape of your decision boundary is affecting people's lives. Right? We're automating all these systems. If you don't know what a decision boundary is, you've got a problem. Right? That's how I think about it. Because if there's a black box and we're orchestrating our entire society around these black boxes, laws written by people who don't understand the black boxes, they're not actually black boxes, right? If you know how machine learning works, it's not a black box. It's a matrix multiplication. And you fit the parameters, right? And there's biases in data, and understanding how that whole picture fits together, I think, is very important. Because of that reason. Because it has real implications in business decisions, we just need to be very thoughtful about how we're building these systems. And I think, understanding, maybe you don't need to know the latest updates to Python APIs, right? That's not relevant. But knowing, what supervised learning is, or what validation is about, or bias and variance at a high level, so you can at least talk about these ideas. They're going to be very important in the future. Yes?
Would you be able to share the slides at the hands-on intro?
Yes. I'll share. I'll put a link to that in this notebook at the top.
Okay.
And this notebook is, you guys can just, that's there. Feel free to use whenever. Yeah, I'll put the slides in there as well. Cool. So if anyone, I guess I don't know how we want to form groups. The original plan was to do it over lunch, but one way to do it is, if you're drawn to one of these data sets, where'd they go? If you're drawn to one of these data sets, to kind of form around that, self-organize there, or it's fine for multiple people to be working on an individual data set. You're going to be taking different approaches anyway, so feel free to purchase however you see fit, and I'll just be powering around. Yep.
Talking about sort of like driving decisions, so with that churn example that you did, is there a way of sort of lifting, opening that black box and understanding what was driving, like the key features that were driving that decision?
Really good question. So in principle, you can look at the weights of the model and get a sense of how important it thinks each feature is. But that's only highly interpretable for a linear model, right? As soon as I throw in that sigmoid, it's like a little confusing what the hell's going on. Like I can tell someone, hey, it's 0.8 times the number of credit defaults they've had in the past 12 months. It's very important. Okay, 0.8 times that makes sense. It's an important feature. But if you pass it through a nonlinearity, what's going on? Increasingly true with deep learning, where it's like millions of parameters, there's no introspectability. So what people are doing is trying to develop sort of a science around model explainability, where you can ask questions of the model about the space that it runs, basically. And that's an active domain of research, a very interesting domain of research, very relevant to HubSpot in particular, because say you tell someone, these leads are good to go after and these ones aren't. That's my job. Right? My job was to figure out which leads are good. So why are you saying this? I want the model to be explained. So huge problem in industry, people trying to figure it out. Cool. Yeah, I don't know how to encourage group formation beyond this. But yeah, feel free to stick around and work on stuff and ask me questions. Thanks, guys.